All right, so this is chapter 6, talking about energy and chemical change. All right, thermal chemistry. Thermal chemistry, the chemistry of um, things that release energy. And thermal means heat. So when energy is released or absorbed, heat also comes in or out of a substance. And we'll talk more about what that means, heat. All right. First of all, let's get a little bit of a foundation on energy. I think probably most of you have learned this in some other classes somewhere, but there's a couple types of energy. Um, all of the energy can be kind of divided into two groups: kinetic energy and potential energy. Kinetic energy is the energy of motion. Potential energy is energy that's stored up. And an example that they use a lot is like a big rock that's at the top of a cliff and it falls down, and that energy at the top of the cliff, the rock has lots of potential energy, right? And that's one way to kind of think about it. And we'll talk a little bit more about what potential energy means in terms of um, uh, chemicals as well, because potential energy is the energy that a chemical has. Now, not all chemicals have a significant amount of potential energy stored in them. For example, if we take a match and we put it on water, it doesn't light up. The water doesn't do anything. It just fizzles away. That means that the potential energy in water is different than, let's say we take a match and put it in a tank of gasoline. The gasoline will start on fire. The energy that's in the water is lower than the energy. And what kind of energy is this? It's potential energy. It's the energy that's stored in there. It's lower in the water than it is in the gasoline. There's a lot of energy stored in that gasoline. And potential energy, when it's stored inside a chemical, we call it chemical energy. All right? So chemical energy stored inside the chemicals, it's potential energy. And you can think about it. You know what happens when some gasoline, Ch6, get this. I'm going to play C8H18 reacts with oxygen. This is one we've been over before. The products are carbon dioxide and water, right? And C8H18 has lots of energy. That's an octane. That's the gasoline, right? We talked about its potential energy. And water is one of the products that doesn't have much energy. And we know that this process gives off a lot of energy. So it's how the atoms are organized which determines whether or not they have the kinetic energy. This formation here, has a lot of potential energy. This one, when an oxygen is with two hydrogens like that, not a lot of potential energy. Same with carbon dioxide. It's something that's floating around. It's not flammable like another gas we know of, like hydrogen gas or oxygen gas. These are two flammable things, right? So the potential energy is stored in chemical energy, and chemical energy has to do with how the atoms are arranged in the molecules. Okay? Breaking bonds requires energy, and when you form bonds, energy is released. We'll talk more about that as well. Okay, in the future. Okay. Let's see. The law of conservation of energy. Energy, like mass, we've talked about mass before. You can't create or destroy mass. Energy can't be created or destroyed either, right? So you can convert energy from kinetic energy into potential energy. When I had my chemical reaction here, the energy changes. It was potential energy, and now it comes off as heat energy, or maybe if this is happening in the cylinder of your car, it's making work energy occur because it's pushing that piston, but the energy is being shifted from potential to kinetic. All right, the units of energy. The joule is one of the different units of energy that we use. There's the joule, and one that we're more familiar with is the calorie, right? We talked about looking at the back of candy bars and finding out how many calories there are, making sure we don't eat too much food, right? That's energy, right? If you store a lot of energy in your body, that makes you plump, right? So we're looking at joules and calories. Now, joules. A joule, the units for joules are kilogram meter squared per second squared. Now, I'll let the physics class teach you a little bit more about those units and what that means. But essentially, energy has the ability to take kilograms and move them a certain distance, move distance, in a given time. All right. So there was an argument about, does it take a jogger more energy to run 2 miles in 10 minutes or run two miles in 20 minutes? And some people said, well, 10 minutes takes a certain amount of energy, 20 minutes takes less energy, but it's a longer time. Okay, but it's not related. That's not the case, because when you take if you're doing something extended over a longer period of time, but you're not extending as much work, then it actually requires less energy. All right, because energy has to do with force, and the speed at which you do things changes the energy. So it's not just moving the mass; it's moving the mass over a given time frame. All right. Joules, oftentimes, because joule is kind of a small number in terms of comparing stuff. If I have a little bit of gasoline and I burn it, it actually releases quite a few joules. So often it's expressed in thousands of joules, called kilojoules. Just like kilometer means thousands of meters, right? So kilojoules are a unit that we'll use quite frequently. The other unit of joule or energy that I mentioned is a calorie. All right. Now we don't use the calorie very much in this class, in this chapter, in this class. We usually talk about joules or kilojoules, but calories are something that you use in the nutritional world, and throughout life we talk about calories on the back of our soup or whatever it is we're eating, right? Now, calories. What is a calorie compared to a joule? 1 calorie is 4.184 joules. 1 calorie is 4.184 joules. All right, that's a definition. We've defined that. 1 calorie is also the energy needed to take 1 gram of water and raise it 1 degree Celsius. So if I had 1 gram of water, that's a little small amount, and I want to raise it 1 degree Celsius, it would take 1 calorie, or 4.184 joules of energy. Okay? That number ends up being kind of important later on, because a lot of the experimentation that we do, the chemistry, is in aqueous solutions, and raising the temperature of aqueous solutions ends up being important. All right. So, a nutritional calorie. When you look on the back of a food and it says that if this product contains this many calories per serving or whatever, they're not talking about the calories that I'm mentioning now. They're actually talking about a nutritional calorie, which is calorie with a big C. And that's how you'll be able to identify the difference if you get into nutrition. Calories with a little c are what I've described here. 1 calorie, little c, 4.184 joules. 1 calorie, big C, the stuff you see on the food, is actually 1,000 calories. It turns out that if you eat a candy bar that contains 200 calories with a big C, it's actually 200,000 kilocalories. But just to save printing space, they start working with calories with a big C, and they call them nutritional calories. But they're actually kilocalories compared to chemistry's regular calories. So we can convert calories into kilojoules, all right? Or vice versa. So here we're going to convert 175.2 kilojoules into nutritional calories, all right? And so you should take a second now, pause this video, see if you can do it, go back a couple slides, see if you can find the conversions necessary, and see if you can convert 175.2 kilojoules into nutritional calories, all right? We're going to perform this right here. Hopefully you can follow along okay. I'm looking for nutritional calories. That means I'm going to make that kilocalories, because 1 nutritional calorie is 1,000 calories. All right, and I'm going to draw my line. I'm going to start with here 175.2 kilojoules of energy, kilojoules, and then I go from kilojoules. I can go from kilojoules to joules. There's 1,000 joules in every kilojoule. And then I go from, my units are now in joules, and I can go to joules to calories. It's how many calories per joule, do you remember? 4.184. So it was other way around. 1 calorie is 4.184 joules. Does that make sense? Then we're going to go from calories to kilocalories, and that's 1,000 calories for every 1 kilocalorie. So it could have, here's another example of a conversion here where you could have gone from kilojoules to kilocalories and then kilocalories to calories. So we should get 41.87 calories. All right, excellent. Now, we also have to have a little bit of a fundamental understanding about temperature and heat, okay? Temperature is the average kinetic energy of all the atoms or molecules, whatever it is, that are moving within that substance. So if I have an example, a cup of water, and it's at 25 degrees Celsius, I can put my finger in there and I can feel how fast the molecules are moving, which is the same in our understanding as kind of feeling how warm the water is. The faster those molecules are moving, the warmer the water will feel to touch. All right, that's temperature. It's the average kinetic energy. Now, heat is the movement of this kinetic energy from one system to one part of, or one entity, one group of molecules, one system to another. For example, if I have 2 blocks of metal and they're at different temperatures, as soon as I bring them into contact together, the heat of the one will start to warm up the cold one. And this is an example of heat transfer. So here you see we have a cold block and a hot block. And when they come in contact, the hot block, the molecules in the hot block, which are moving faster, begin to speed up the rate at which the cold block molecules can move, or units, or could be, atoms, molecules, whatever the chemical unit is. Okay, until we reach, which is called equilibrium, thermal equilibrium, where all the 2 blocks now are the same temperature. This is how heat transfers. So heat always has to transfer from the hot thing to the cold thing. Okay? So the movement of heat moving from hot to cold, is the movement of kinetic energy, of the movement of the molecules. All right. Big E is a unit which we use, which we call internal energy. It just means all the energy of the system. The energy that's kinetically moving around, that's the temperature, and also the energy that's potentially stored in that chemical, and that's usually within the chemical bonds that are between the atoms. And like we said, you take some molecules, burn them, and then a reaction occurs and the chemistry changes. And that process releases some heat energy sometimes, and so that it's evidence that there was some potential energy in those molecules. All right? If we ever want to find the change in energy of a system, we can have the energy, or we can have the system and measure its total energy, let's say, and then we can do some sort of a change, whether it be a reaction or waiting for time or whatever, and then we can measure the energy afterwards. So we have what we call our energy initial of the system, and then after the change, whether it's a reaction or time or whatever, we can measure the energy afterwards, and that'll be called our energy final. So energy initial and energy final. And the change in energy that occurs will be the final energy minus the initial energy. Okay? So if the energy goes up, if it starts at 10, the energy starts at 10, and then later it's 20, then the change in energy would be the final energy, which was 20, minus the initial energy, which is 10. And so the change in energy would be, in that case, a change of 10. So the energy final minus the energy initial, right, equals the change in energy. So if my final energy was 20, and my initial energy was 10, 20 minus 10, my change in energy is 10. So it's always final minus initial. Final minus initial. For a lot of things, not just energy, that's for temperature as well. If temperature changes, to determine the change in temperature, you always take the final temperature minus the initial temperature. All right, for a chemical reaction, we can think of it then as the energy of the products minus the energy of the reactants. All right, so here I have my favorite reaction that we've talked about lots of times, right? C8H18 plus oxygen gas forming water and carbon dioxide. All right, have that chemical chemical reaction. All right, so we can take the energy of the product. So here's a chemical reaction, AB going to AB like this. We can take the energy of the products and subtract it from the energy, the collective energy of A and B, the sum, right? And that will be the change in energy for the reaction. Okay? All right. Now, um, a little bit of a recap. Temperature, that is the average kinetic energy for the system. The kinetic energy of all the molecules. We call that temperature. And we have measurements which can, tools, thermometers, which can measure how much the movement of the molecules is, and we call that temperature. The internal energy, big E, that's related to the movement, the kinetic energy, and also to the potential energy that those chemicals might have. Okay? If we look at this plot here, this is an interesting plot, something you see kind of frequently where they plot the fraction of on the y-axis, the fraction of the total numbers of particle having a particular kinetic energy, and then the kinetic energy, what kinetic energy they have on the x-axis in just some arbitrary units. So you see that the purple one, more molecules on the y-axis, the number of molecules, right? More molecules have a lower kinetic energy. Whereas in the yellow one, more molecules have a higher kinetic energy. So the question generally is, which has the higher temperature? And a lot of times people want to say, oh, one, because it has, purple goes higher. The purple one because it goes higher. But that's not how you identify the temperature, right? Temperature is the higher kinetic energy. And so it would be the second curve, the yellow curve. The purple curve, more molecules have that lower kinetic energy, but that's not, the y-axis isn't what we're interested in. We're trying to find out here who has the higher temperature. And because the higher the kinetic energy, the higher the temperature, the yellow one there has the higher kinetic energy, or higher temperature. Does that make sense? Did you follow that? Not really? Kind of confusing? So you have the purple graph and the yellow graph. The purple graph on the y-axis, it's measuring the fraction of the number of particles. So, what percentage you can think of it as. And the purple graph, you see that most of the particles, right where the 1 is pointing at, the little 1 bracket there, most of the particles have that much kinetic energy, which looks like around 2.5 on this scale. Does that make sense? Whereas the yellow one, most of the particles have kind of near we draw that here so we can discuss it. Does that make sense? So there's this, and then there's this sort of thing. On the second curve, most of the particles, this is the second, this is the first one here. Most of the particles have this much kinetic energy, all right? And again, kinetic energy is higher temperature. So the more particles that have the higher kinetic energy, it's going to have the higher temperature. All right, so kinetic energy, I don't know if you've heard this before, but probably somewhere in a physics class at high school, or maybe a chemistry class at high school, science class of some sort. Kinetic energy has a very popular formula, which is 1/2 mv squared, where the kinetic energy is 1/2 m, which is the mass of the particles, times its velocity squared. So the more massive a particle, the more energy it can have, right? And that makes sense, because if I have a bus moving at, let's see, a velocity of 20 miles an hour, compared to a child on a bike, Tommy riding a bike at 20 miles per hour, the bus is going to have a lot more energy, be a lot harder to stop, right? I could grab little bicycle boy, but the bus, I couldn't stop if it was going 20 miles an hour, right? I don't know about 20 miles an hour. I don't know if I can stop anybody on a bike either, but you can imagine them having different energies. So just because they're moving the same speed doesn't mean they have the same energy, because mass is a component. Does that make sense? And on the same hand, if I had a train moving at only, 0.5, a half a mile every hour, that's pretty slow. And I had a boy moving at 5 miles an hour on a bike, I could probably stop the boy, but I still might not be able to stop the train, even though it's moving very slow. So it's not, there's both the speed component and the mass component, right, that you have to take into account. Okay? Or a bullet moving very small mass, but 200 feet per second or 1,000 feet per second, I wouldn't be able to stop it, right? Even if I caught it. Okay, so cold objects, we say they have lower average kinetic energy. Hot objects, higher kinetic energy. All right. Now, these functions or these types of characteristics of systems, like the temperature changing, final to initial, or the energy changing from final to initial, we call state functions. You can identify how the temperature is, or how the characteristic, whether it be energy, temperature, we show a few others here, pressure and volume. These change, and as these change, then you can tell by the final volume to the initial volume, or the final temperature to the initial temperature. You can see how that change has occurred by looking at final minus initial. And anything that has that property, where you can look at the final minus initial, is called a state function. All right. Another way to think about it, which is kind of abstract, is the small little components, the small little parts that actually made that temperature change or that volume change occur might not be recognizable, but that's okay. If you just look at the final minus initial, you can still collect the energy you need to, or the information you need to. Okay. Temperature is our example. Temperature final minus temperature initial is how we look at the change in temperature, and that makes sense for us. If I have a system that starts off, it's here it is. It's a glass of warm water. All right, it starts off at 90, we'll say, degrees Celsius. That's pretty hot, right? 90 degrees Celsius. Starts off at 90 degrees Celsius, and then I let it set for a while, and I come back and measure it later, and its temperature is now 50 degrees Celsius. All right? I would like to see how the energy has changed. How has the energy changed in this system? And what did we say we needed to do? Take the final minus the initial. So if I take the temperature final, which is 50, minus the temperature initial, which is 90, then my resulting number is a minus 40, right? Minus 40. So temperature doesn't relate directly to energy like that, but we can see that it lost energy, and that loss of energy is embedded in that negative sign there on that 40. That makes sense? The system has lost energy, so we say negative 40 is the answer. And that'll always be negative if you take the final minus the initial, and the system has lost energy. If I started at 10 degrees Celsius and I went up to 50 degrees Celsius, then what would I see? 50 minus 10, that would be a gain of 40 degrees Celsius. Energy has been put into it, and I could be reminded of that by looking at the positive sign that's in front of that 40 now. Okay? So the negative and positive sign is important. Now, we have to have a little conversation about some systems, because always we're answering questions about the system that we're working with, right? If I have a beaker and I have some water in it, then that beaker can evaporate and lose some of the molecules into the air. So then I have to kind of think about that, take that into account. If I close the top, it might not be able to lose molecules into the air, but it could still lose temperature into the air that's surrounding it through the glass beaker, right? So I have to think about how it could lose mass or lose energy, right? Why do we care about it losing mass? Well, if it starts off at 100 grams, now let's think about it. We said that a calorie, or 4.184 joules, was how much energy was necessary to raise 1 gram of water 1 degree Celsius, right? So if I start off with 10 grams of water and I want to raise all 10 of those grams 1 degree Celsius, I can now calculate how much energy I would need to do that. But if in the process I start losing mass into evaporation, now my mass is changing. So the amount of energy that's going to be required is going to be different. Does that make sense? So I have to kind of take that into account if I ever wanted to do that sort of an experiment. So we have to think about what the system is like. When we identify a system, we can separate the system from its surroundings. The system is the portion that we're interested in. The surroundings is everything else. And the scenarios that I described, you can move heat from the system to the surroundings, and sometimes you can lose mass from the systems to the surroundings. The boundary would be, where the system and the surroundings meet. So here's some examples. Here's an example of an open system, just a beaker, and often, usually that's what we're working with. Just some sort of a system, and it's open to the surroundings. And like I explained, mass can move in and out of that, and heat can move in and out of that as well. Here's a closed system. A closed system, we have a lid on it. Can mass move in and out? But can temperature move in and out? Yeah. Or heat, sorry, not temperature. The temperature can change, and that would move heat in or out. I could bring in something warm, and it might warm up my system. Or if the system, or the closed reaction heated up as the process proceeded, then it would release heat, and that could warm up the surroundings, right? So a couple of examples. All right, so the other type of system is what we call a isolated system. In an isolated system, you don't get heat or mass moving from the system to the surroundings, right? So this would be like a thermos or something, where you have a lid on the thermos tight, so mass can't leave, and it's insulated. So any heat that is coming from the outside won't affect the inside, and the inside is all trapped in. That make sense? Anytime you do a process under those conditions, we call it an adiabatic process. Adiabatic. No heat is allowed to leave, and no mass is allowed to leave. Heat. Now, energy was big E, right? Internal energy. The whole energy of the system we identified as big E. Heat energy can actually leave in a couple ways. We can have it leave in heat energy, or it can leave in work energy. All right? I can push you, and that would require a little bit of energy from me, and it would increase your energy a little bit, right? If I took your hand and rubbed it like this, you would get hot from that energy, and that release of my movement and work would be losing me. I would be losing energy, and you would be gaining it, right? So I can transfer heat in a couple ways, work or heat. Heat, we give the variable Q. All right, so Q. And Q is directly proportional to the change in temperature. So let's write this down. Heat, Q, equals the change in temperature. Do you agree? So the temperature goes up. That means the heat was being transferred in, right? If the temperature is going down, what does that mean? The heat has been transferred out. Is that correct? All right, there's a direct relationship. Heat goes in, temperature goes up. Now, you might know that just because something is heated up a certain amount doesn't mean that its temperature is going to change the same amount. If I had a teaspoon of water, here's my teaspoon of water, right? And I had Grandma's pool. All right, there's Grandma's pool. Here's the diving board. She doesn't have a diving board, but just so you can see the scale, there's a person on the diving rock or whatever it is. Okay, so here's the pool, and here's the teaspoon of water. If I give them the same amount of heat energy, which one is going to heat up more? This one? Why would the teaspoon heat up more? Less mass, that's right. So you need to keep in mind that not everything will make the same change in temperature with the same amount of heat added. Will this change temperature? It will change temperature, but it'll change less than this one. So there's always going to be an increase in temperature when you increase the heat. But the change will not just be always the same amount because it's dependent on the mass. It's also dependent on the substance. Maybe I don't have two hugely different masses of material, but maybe I have two blocks of, this one might be gold, and this one might be a block of plastic. All right. All right. So I have this. I'm heating up these two systems. This one is gold, and this one is plastic. And we talked about how if the mass of the system is different, then the amount of heat that you add will change the amount of temperature. It'll still raise the temperature, but it'll change the amount. Larger systems require more heat to change the temperature. But it also depends on the type of material you have. A piece of plastic, even if it's the same mass as the gold, will not increase its temperature as much when you add the same amount of heat to it. All right. So we call that the mass of the material and the kind of material it is. We lump that all together and we identify what's called a heat capacity, C. C. C is how much energy, how much heat energy is needed to raise that system, whatever it is, and that system again takes into account its mass and the kind of material it's made of, how much energy it requires to raise that system 1 degree Celsius. Okay? So, the heat capacity is always how much energy, and energy are in joules, how many joules it requires to raise that system 1 degree Celsius. So it's how many joules per degree Celsius. That's what the units are for C, which is heat capacity, the capacity of heat necessary to raise it 1 degree Celsius. All right, so we have to sneak that into our equation here. Heat equals the heat capacity times the change in temperature. All right, so if it raises, let's look at the units now really quick. Heat is in units of joules. Heat capacity, we said, was how many joules for every degree Celsius that actually changed. And change in temperature is going to end up being in degrees Celsius. Right? So when I multiply joules for every degree Celsius, and I find out maybe it raised 10 degrees Celsius, multiply these together, my degrees Celsius is cancel out, and I'm left in joules. Okay? So if you know the heat capacity for that system, and you know how much temperature it changed, you can solve for the heat. And if they tell you how much heat you're going to put in, and you know the heat capacity, you can predict how much the temperature will actually change. Okay? Very good. So, we talked about this. Just a quick review. The heat capacity is the amount of energy that is required to raise that object, which includes its, all of its mass and the material that it's made of, all together in one thing called the heat capacity. And the units for heat capacity are joules per degree Celsius. All right. So, if I have a cup of water, we're going to use it in the experiment, and the heat capacity for that cup of water, that means the cup, the water, the mass, everything combined, is 720 joules for every degree Celsius. Okay? How much heat will it absorb if the temperature changes from 19.2 to 23.5? 19.2 to 23.5. Well, we know that the heat is related to, or is equal to, the heat capacity times the what? Change in temperature. Now, where do we get the change in temperature? Change in temperature equals temperature final minus temperature initial. Very good. So the temperature final here, what's our temperature final? 23.5. 23.5 minus our temperature initial, 19.2. What is that? What does that equal? I don't have my calculator. 19, 20, 21, 22, 23. That's 4. 23.5. 4.3. All right. So 4.3 degrees Celsius. That is our what? Change in temperature. That's right. 4.3 degrees Celsius. 4.3 degrees Celsius. Now that's related to how much heat must have been released, right? Or in this case, yeah, how much, what the heat absorbed by the system. So I have to multiply this 4.3 by what? The heat capacity. Now here is where they give us the heat capacity, which is 720 joules per degree Celsius. All right, so let's see how this works. 720 joules times the 4.3, and that will tell us how many joules of heat energy the system absorbed. Now, the answer here, 3.1 times 10 to the third, is a positive value. It's a positive value. So that's, again, a reminder that the heat was absorbed by the system, right? And we could think about it, what would it take to make that system, or that a negative value, to show that the heat was lost by the system? Well, you need to change this, right? The temperature change would need to be different. It would need to be a lower final temperature. And that would make sense. If it started off at 19.2 and then went to 23.5, no, sorry, other way around. If it started off at 23.5 but then went down to 19.2, that would be losing energy, right? So this would become a negative number. And then when you multiply this negative number by the heat capacity, it would be a negative heat. And so there would be how much energy in joules that the system lost. So the fact that it's a positive value is another indicator that this is energy that was gained by the system. All right, here's another one. If it requires 4.184 joules to raise the temperature of 1 gram of water, 1 degree Celsius, what is the heat capacity of the water? What's the heat capacity of the water? Well, I know that the heat is equal to the heat capacity times the change in temperature, right? And if I want to change the temperature of the water 1 degree, right? 1 degree, so I can make the change in temperature 1 degree Celsius. How much heat energy is that going to take? If I want to change 1 gram, 1 degree Celsius, it's going to take 4.184 joules. 4.184 joules. Very good. Now my C here, what are the units for C? Do you remember? Units are how much energy for what? Every degree Celsius, right? So that is units of joules for every degree Celsius. So I can solve for this. I mean, it's like saying 4.184 equals x times 1. And I can divide both sides by 1, right? Get rid of that, and x is going to equal 4.184. And the units here are going to now be joules per degree Celsius, because this was degrees Celsius, and this was in units of joules per degree Celsius. Okay, so let's see that here. I have 4.184 joules. That's how much it required for 1 degree Celsius. So that is my heat capacity of water. So you can use this type of equation to identify the heat capacity of the water. Now, you're going to say, do I have to memorize this equation? Well, if you're going to think about it that way, yeah. But if you just think about it, the logic that you already know, the amount of temperature that's changed is due to heat coming in or out. You already know that Q equals the change in temperature. You also already know that you have to know how much energy it requires to change that system 1 degree Celsius, because that's dependent on a lot of different things, right? Mass and the kind of system it is, the kind of material it's made of. All right, so here's another one. You guys can pause it if you want to, work through this one, and try to get the answer. I'm going to give you the answer in 5 seconds. 5, 4, 3, 2, 1. All right, hopefully you got that one right. Okay. Here's another one. Copper mug has a heat capacity of 77.5 joules for every degree Celsius. After adding hot water to the mug, the temperature of the mug changed to 77, or from 77 to 185. How much did the mug absorb from the water? Okay. We can get our change in temperature there. We know the heat capacity. Can you see the heat capacity? You want to point to it? That's right. That's the heat capacity. We know the heat capacity. We know the change in temperature. Now, some people might not remember how to subtract those two numbers and get the change in temperature. It's change in temperature what? Temperature final minus temperature initial. That's right. So that would be our change in temperature, and then we have our heat capacity. All right, so got 5 seconds. See if you can get it. I mean, you can push pause right now and take your time. Okay, I'm going to reveal it now. So if you haven't pushed pause and you want to take your chance to do it. All right. Good deal. Ooh, a little bit tricky. Didn't recognize that. That the change in temperature is in Fahrenheit, but because the heat capacity is in joules for every degree Celsius, you would need to convert that Fahrenheit to degrees Celsius. So, a little trick problem there I should have warned you about. All right, so specific heat. Specific heat. We're going to introduce a new thing called specific heat. Specific heat is for systems that you don't know the heat capacity for, right? If you don't know the heat capacity for the system, then what would you have to do? Well, you could take the system and raise it 1 degree Celsius and find out how much energy it required. Or you could do the calculation yourself just by looking at the mass of the system, because the heat capacity is equal to the mass of the system times what we call the specific heat. The specific heat. And that's the energy, or sorry, that's the property of the material that it's made of. So water has a specific heat of 4.1 grams or joules for every gram. That's going to raise 1 degree Celsius. And the units for specific heat is how much energy, joules, is required to raise not just the thing 1 degree Celsius, but every gram of it, 1 gram, 1 degree Celsius. So the units for specific heat are joules per gram degree Celsius. Okay? All right, so then, if we're told that the specific heat of water or we want to calculate the specific heat of water if we know that the heat capacity is 100 grams. We know the heat capacity of 100 grams of water is 418 joules per degree Celsius. So in this one, we're given C, the heat capacity, and we are given the mass of the substance, and we want to identify what S is. All right, the heat capacity is 418, the mass is 100, and we can define that. Okay? And that'll tell us the specific heat of the water, S. What's the specific heat? What is the specific heat of water if the capacity is 1 gram? A capacity of 1 gram of water is 4.18 joules per degree Celsius. Well, the specific heat of a material doesn't change, right? Because it's the same. It's the same. The specific heat of water is always going to be 4.18 joules for every gram for every degree Celsius. Now, the heat capacity of a system can change because a new system might have different masses or be made of different materials. But when you're talking about the specific heat of a material, you're talking about just that one thing, like water, ethanol, iron, gold. The specific heat, meaning how much energy is required to raise 1 gram of that 1 degree Celsius. So the answer is going to be the same here. And if you do the calculation, you'll see why it's the same. Okay. If I know the specific heat of silver, it takes 0.235 joules to raise every gram 1 degree Celsius. Is that more energy or less energy than water? 2.235 joules of energy to raise 1 gram of silver 1 degree Celsius, right? What was it for water just now? Do you remember? It was like 4, right? 4.13, what was it? 4.18 joules for every gram to go up 1 degree Celsius. But this is only 0.235 joules for every gram to go up a degree Celsius. So, was it easier to heat? Water or silver if you have the same masses of the material? It's easier to heat the silver. That's right. The silver will raise up temperature faster. So we want to identify the heat capacity of a 100-gram sample. So C equals, it's the mass times the specific heat, where the mass of the sample. All right, so before we answer this question, we're going to have a quick review. All right, heat capacity. Heat capacity is something that we know the units for. Its units are, what are the units? Its units are joules for every degree Celsius, right? Heat capacity. It's how many joules of energy you need to change that thing 1 degree Celsius. All right? So, if that's what heat capacity is, well, what's specific heat? Well, specific heat is not just for systems, but for certain kinds of material, right? You know, the material. So if I have the specific heat of a material, then it's how much energy is required, joules, to change its temperature 1 degree Celsius. But we also need to know how much mass of that material you have, because the amount of energy required depends on not just the change in temperature, but also the mass of the material. So we need to know how many grams or so joules for every 1 gram, the amount of energy for every 1 gram to change 1 degree Celsius. Okay, so now we can say the specific heat of silver is 0.235, and its heat, what is the heat capacity of a 100-gram sample? Okay, we're looking for heat capacity, and we know that the mass times the specific heat will give us the heat capacity. So I can identify the answer there pretty easily, right? So this is a list of some specific heats, and you see that things like water, down at the bottom of the list, have pretty high specific heat. It requires a lot of energy to make the change in temperature. All right, so how can we use these specific heats? Well, we can use the specific heat, S, in an equation like this, where if we want to identify the amount of heat energy required, we take the specific heat, we multiply it by the mass of the material that we have, and then we can multiply that by the change in temperature, and that will give us how much heat energy was required for that process. All right, so this one here, you can take a few seconds to solve it if you'd like, but I'm going to move by it, so push pause if you want to take your time. Okay, and then this one here, the specific heat of copper, metal, is given to us, and we want to know how many joules of heat are necessary to raise the temperature of a 1.42 kilogram block of copper from 25 to 85 degrees Celsius. We want to know how much heat is required. I want to know how much heat is required to change this block of copper. How much copper is it? 1.42 kilograms. That's the same as 1,420 grams. So that's the mass of our system. What is the material? Or in other words, what's the specific heat? Specific heat is 0.385 joules for every degree Celsius, and for every gram. I'll switch those up because that's the way I've been writing it previous. Gram degree Celsius. That's how many joules it requires to raise 1 gram 1 degree Celsius. This is the gram that's going to, the mass that's going to be raised that amount. And how much is it going to be changed? Well, we have to take final, 88.5 minus initial, 25, and that'll be our change in temperature. Okay, so here we have our change in temperature, which was 63.5 multiplied by our specific heat times the mass. So make sure you can do that in your calculator. All right, heat flow. We talked about before that heat always goes from the hot thing to the cold thing, right? Because that's the way heat has to flow. Now, for this to occur, it's all about the movement of molecules, right? And for us to kind of define it, we use the values, the positive on our Q to say that the system is increasing in its energy, and we use the negative on the Q to say that the system is losing energy. So the amount of heat that is gained by the system is equal to the amount of heat that is lost by the surroundings, and vice versa. If I have a cold cup of water, let's say it's at 4 degrees Celsius, and I sit it in a hot sun, and now later it becomes 29 degrees Celsius, all right? The change in temperature is 29 minus 4, or let's go to 24 to make it easy, 24. 24 minus 4, there's a 20 degrees Celsius change in temperature, right? I can identify how much heat was required to make this process occur by, again, Q equals ms delta T. The mass of the water, we'll say that's 10 grams. The specific heat of the water, 4.184 grams for every, 4.184 joules for every gram degrees Celsius. All right, and the change in temperature was a positive 20 degrees Celsius, final minus initial. So 20 times 4.184 times 10 would tell me how much heat the system gained. And this Q would end up having a positive, would be a positive number. And that's what I wanted you to recognize, that when a system gains heat, then the Q is positive. If I looked at the surroundings, maybe this was in a contained box of hot air, well, as the water gained the temperature of the air goes down. The temperature of the air cools down, and the amount of energy, the positive Q here, that the water absorbed would be the same amount of energy that the surrounding air would have lost. All right, so you take a piece of warm iron, you put it into a beaker of cold water. The iron loses the 10 joules of heat, but the water gains the 10 joules of heat. Okay, so who would have the negative sign, the water or the iron? Q is the same for both, 10 joules of heat. Who would have the negative sign? Well, the iron has lost that energy, so it would be a negative 10 joules of heat for the iron and a positive 10 joules for the water. All right. How about this one? A cast iron skillet is moved from a hot oven to a sink full of water. Which of the following is false? The water heats, the skillet cools, the heat transfer for the skillet has a negative sign. The heat transfer for the skillet has the same sign as the heat transfer for the water. Which of the following is false? You can think about it for a while and push pause if you need to. Okay, so the heat transfer for the skillet has the same sign as the transfer for the water. That's not true. They have to have different signs. Now, the amount of heat that they lost and the amount of heat that was gained by the other is the same, but they have to have opposite signs. Okay. So here's an example of a problem where we take something that's hot, we drop it into 250 grams of water. The water warms from the hot piece of metal that's dropped in the water. And we want to know the heat capacity of the ball bearing that's dropped in the water. Okay? So read through that for a second. Push pause if you need to. The heat capacity of the cup is 1,046 joules per degree Celsius. And we need to identify the heat capacity of the ball. Well, they didn't tell us much about the ball. Did they tell us the mass of the ball? No, they didn't tell us the mass of the ball. Did they tell us they told us the temperature of the ball, right? But how can we learn about the energy of the ball, the system of the ball, if we don't know about the energy of if we don't know anything about the ball? Well, we know that there's a relationship between the heat that is being lost by one of the entities and gained by the other. So something has a positive Q, and the other thing has an equal but opposite negative Q. So who has the positive Q here? Who is gaining the energy? Well, the water is. The water is warming. Who's losing the energy? The ball bearing is. The ball bearing is losing the energy. And however much energy is lost, the same amount of energy is gained by the system. Okay? So, we can see that Q lost by the ball bearing is equal to the Q gained by the water. Okay? Let's see. The Q lost by the ball bearing equals the negative Q gained by the water. Now that's true. We should have had the negative sign over on the lost by the ball bearing, though, because it's losing the energy. But it's true that whatever one you want to put the negative sign on is fine, because it's just an opposite sign. Okay. We can identify the change of energy, the change of heat from the water. All right. We can identify the heat change for the water, and that will tell us how much heat was lost by the ball bearing. So what did the water do? It went from 37 to 37. It went from 25 to 37.3, right? And we know it's the heat capacity of the cup of water is 1,046 joules for every change in degrees Celsius. So how much did the change in temperature be? Well, it's 37.3 minus 25, right? So that's 12.3 degrees Celsius, right? That's the change in temperature, 12.3. It's a positive value. And apparently the heat capacity of the cup, again, 1,046 joules for every degree Celsius that was changed. So we can determine how much heat the water gained by taking the 1,046 joules for every change in degrees Celsius and multiplying it by how many changes in degrees Celsius we had, which was 12.35. And that will tell us how much heat the water lost. The amount of heat that the water lost is also the amount of heat that the amount of heat that the water gained. The amount of heat that the water gained is also the amount of heat that the ball bearing lost. So the ball bearing also lost the same number of joules of energy. All right. So that's the amount of energy that the ball bearing lost, right? It's a negative 12.87 times 10 to the third. We got that from the previous slide, right? It's the same amount of energy. So this is how much energy the ball bearing lost. Now we're going to take that and we're going to see if Q, if that's how much energy the ball bearing lost, the heat there, we know that it's equal to, and we want to know the heat capacity of the ball. It's going to be equal to the heat capacity of the ball times the change in temperature of the ball. Times the change in temperature of the ball. Now, what was the change in temperature of the ball? Well, it's the same. No, it's not the same, right? It started at what? It started at 260 degrees Celsius, and it went down to, where did it end at? It ended at 37.3. 37.3, because that was how much the water heated up, and it stopped heating at that point. So the temperature change is 37.3 is the final, minus the initial, 260 degrees Celsius. All right? So that's a negative 222.7. All right? So if I have that change in temperature, and I know the negative 12.87 times 10 to the third joules, that's how much heat energy was lost by the ball bearing, then I can solve for the heat capacity of the ball bearing by taking my 12.87 times 10 to the third and dividing it by the 222.7. The negative signs cancel out, as should be expected, and then we get the heat capacity of the ball. All right, excellent. So here's one I'll let you try on your own. Okay, push pause if you need to. All right, so in this one, we're going to remember that the Q equals SM delta T, and we identify the heat energy that was lost. Here's another one that you can try by your own. Here, I'll show you that a little bit longer. Here's another one you can try on your own, so you can push pause if you want to try it. Okay, so here we need to find the change in temperature. All right, we use our same relationship, Q equals SM delta T. All right. This is the last one you can try on your own. Push pause if you want to